Good morning, everyone, all the delegates to the ICNI 3 conference in Belgrade. I am sorry that I'm not able to be with all of you today in person. This is something I would have liked very much to do. I'm also grateful to the authorities of the conference for having awarded me this Van der Waals Prize, which is a prestigious award given by your organization. And I hope that in the next 30 minutes or so, I'd be able to give you a brief summary of some of the work we have done ourselves on the nature and function of these Van der Waals interactions, more particularly in crystal engineering. So when one talks about crystal engineering, in other words, the prediction, control, design of molecular crystal structures, we're talking about molecules and crystals. We talk about molecules because molecules are what chemists make. We take these molecules and see how they become crystals. The reason we do this is that these crystals have very interesting properties that are quite different from the properties of the molecules themselves. Coming to Van der Waals, whose name figures in the prize that I have been awarded today, he of course gave us this idea of the Van der Waals forces, which contain this attractive part at short distances and the repulsive part at even shorter distances. And a balance between this attraction and repulsion gives rise to stable crystal structures which correspond to roughly a minimum in the potential energy curve. Now, many of you will know why I have put up this picture of the common garden lizard or gecko. The Van der Waals interactions actually give rise to what is called this gecko effect. Why this lizard is able to maintain itself in seemingly impossible positions, almost vertical, or even walking on the ceiling of a room. The fact of the matter is that the pads of the feet of this gecko contain very fine hairs called cilia, and when these cilia come to very short distances between the surface on which it's trying to walk, these Van der Waals forces maintain themselves. A, they are very weak, and B, they can be broken and made very easily. So at these very short distances, these forces are made, and that is why it's able to stick. And then they can be unmade, which is why it's able to move to the next position. Now, what is crystal engineering? I think most, if not all of you, are aware of this 1989 book that I wrote, The Design of Organic Solids, I called it. Although strictly speaking, the subject has now come to mean the design of any molecular solid, whether it's organic, inorganic, or organometallic. And the popularity of the subject in the first 2 decades allowed me to co-author a book, a textbook actually, on crystal engineering that I'm told has become quite popular. My original definition of crystal engineering seems to have stood the test of time. And the understanding of intermolecular interactions in the context of crystal packing and in the utilization of such understanding in the design of new solids with desired physical and chemical properties. Three phrases are of importance in this definition, and they sort of represent 3 decades of work by a very large number of people who have been interested in this subject. The 3 phrases are intermolecular interactions, utilization of understanding, new solids desired properties. So there is a question of these interactions, how you understand and use them. This is the synthetic strategy in making a crystal. Notice I'm using the word synthesis for the first time. And then you want to make new things with certain properties. So there is an interaction, there is a strategy, and there is a property. So these then are the 3 phases of the subject. Now, the molecule to crystal aspect. I said you start with molecules and you make crystals. The question can be phrased in different ways. Given the molecular structure of an organic compound, what is its crystal structure? The question looks simple, but the answer is by no means simple, because there are no direct ways in going from molecular structure to crystal structure. How do molecules recognize one another? Because this recognition is a key event prior to nucleation and crystal growth. It is, and always has been, a molecule to crystal problem. And the fact that there is no 1:1 direct correspondence between molecules and crystals in terms of functional groups, which is one of the most common ways in which we describe molecular properties. Now let's take an example. I show you the structure of benzoic acid, which in the crystal associates with another molecule of benzoic acid through our familiar OHO hydrogen bonds. Now this dimer structure for benzoic acid, of course, very common, and you see it in a number of aromatic carboxylic acids. Now on the other hand, I take acetic acid. Now acetic acid does not form a dimer. That's the first surprise. I bring in my second molecule and I find, and a third, it does form hydrogen bonds. But the resultant structure, supramolecular structure, is not that of a closed dimer, but an open chain, which we call catamer. Now, why does this acid give a dimer? And why does this acid give an open catamer? It cannot be, therefore, that this dimer catamer depends only on the carboxylic acid group. I cannot say that just because something is a carboxylic acid, it will form a dimer. I cannot say that just because something is a carboxylic acid, it will form a catamer. Dimer versus catamer will depend on the nature of this other group, phenyl or methyl. In other words, this phenyl and methyl group are not forming hydrogen bonds, but they are affecting the manner in which the carboxylic acid groups form hydrogen bonds. So now you see, you're beginning to appreciate the difficulty of this subject. Something sitting in some other part of the molecule is deciding what happens here. This is the problem. So to recapitulate, this is the carboxyl groups of the benzoic acid, and this is how they come together to form the dimer. This is a closed dimer. Now, the same thing in acetic acid. The carboxyl group is the same, but the next one comes to form a catamer. So you see, you have a closed dimer and then you have an open catamer. Now, why the difference? If the nature and number of hydrogen bonds formed by these carboxyl groups is the same in both cases, why are the crystal structures different? The difference must come from the phenyl group, methyl group difference in the two acids. So in other words, a group that is not directly concerned with the important interaction seems to be playing a role in what final crystal structure is formed by the particular acid in question. One of the earliest attempts at addressing the molecule to crystal problem was undertaken by the famous Scottish crystallographer J. Monteith Robertson, who incidentally was the PhD supervisor of my PhD supervisor. In 1951, he classified hydrocarbons as those where the molecular area is small in comparison to their thickness. These are things like naphthalene, anthracene, and so on. And he said they're characterized by a short monoclinic axis in the range 5.4 to 8 angstroms. On the other hand, he said there are those where the molecular area is large in comparison with the thickness, things like coronene, ovalene, and so on, which are characterized by short axes in the range 4.6 to 5.4 angstroms. So here you have a clear classification of crystal properties in terms of molecular structure. Professor Gavazzotti and myself looked at this business in more detail in 1989, and we extended Robertson's studies to a series of 32 polynuclear aromatic hydrocarbons, many of which, incidentally, had been studied by Robertson 40 years prior to our study. Moving on, the big question really is, how do molecules recognize one another from the earliest stages of association towards nucleation and finally crystallization? And if you come back to my first definition of crystal engineering, how can we understand this sequence of events in terms of the interactions? The core problem is that crystal structures cannot be predicted easily from molecular structures. We've just seen that in the case of benzoic acid and acetic acid. So a modular approach, which is so popular and common in solution organic chemistry, does not work in solid state organic chemistry. The behavior of a functional group in a molecule during crystallization depends on the nature of the functional group, but also its positioning. Two factors here are of utmost importance with regards to these functional groups. The first is their nature, and the second is the position. As for the nature, this is obvious. This is important, of vital importance in solution chemistry. And it is what makes a functional group a functional group. Regarding the position of the functional group in the molecule, this can be important sometimes in solution chemistry. We have things like proximal group effects. But it is in solid state chemistry and crystal engineering where the position of the functional group in the molecule has an immediate and direct effect. The position of the functional group is of acute importance. The same group in a different position will have an entirely different effect on the final crystal structure. This is why I say that crystal engineering in general, the study of a complex system like a crystal, is a difficult endeavor. It is not easy because there are many things happening, many factors to consider, and the factors come together in ways that are not often easy to predict. Let's go to a specific example. The crystal structure of, say, 3-aminophenol need not be closely related to those of either aniline or phenol. We have two functional groups here, NH2 and OH. So putting them together in the same molecule makes each of them slightly different. In the limit, 3-aminophenol need not even be related closely to 4-aminophenol in terms of its crystal structure. Now this is something we actually saw, because if you look at these two, this is 4-aminophenol, a molecule studied by Otto Ermer many years back. And here you have a crystal structure which is hydrogen bonded. You have a hydrogen bonding between the OH group and the NH2 groups, a continuous network of supramolecular cyclohexane rings. And then it appears that these rings are actually held together by this hydrocarbon area. Now we are coming more into the regime of van der Waals interactions. So you see, in fact, Kitagerodsky said something on these lines, that hydrogen bonds are formed, but they do not disturb the overall arrangement of the van der Waals interactions in the structure. So it is like the cart and the horse, or the dog and its tail. Is the hydrogen bonding in 4-aminophenol decided by the CH interactions between phenyl rings, the so-called herringbone interactions, or are the herringbone interactions decided by the hydrogen bonds? Kitagerodsky felt that the close packing forces, the van der Waals interactions, would be determinative. And it seems that at least in this case, he was correct. Because when you go to 3-aminophenol, the nice OH and NHO hydrogen bonds, you don't find it anymore. And in fact, you find now a totally different kind of interaction, a new one that we've studied with neutron diffraction and other things, the so-called NH-pi interaction. So, whether the hydroxy group and the amino group are located in a 1,3 orientation or a 1,4 orientation makes a complete difference in the kind of crystal structure that is formed. So you can almost see that it looks like it is the aromatic rings and the positioning of these functional groups that determines the final hydrogen bonding itself in the structure. The 3-aminophenol would well do without NHO and OHN in order to form the NH-pi interaction here. So it's an interesting example, and one that we studied about 25 years ago. Now, so coming back to the problem, crystal structures are not related to molecular structures, functional groups, in simple ways. They are what are called, using the language of complexity, emergent properties, things that are not always easy to predict. In other words, the property of one molecule may or may not be the same as the property of a few molecules, which may or may not be the same as the property of many molecules, which may or may not be the same as the property of the crystal. In other words, when you're building up the crystal in some kind of an Aufbau-like process, we don't really know how molecular crystals are built up. Are small clusters formed which increase in an orderly way to give larger clusters? Or are the events more irregular? In other words, irregular means many is not modeled properly by few, and crystal is not modeled properly by many. So depending on the size of the cluster, the nature of the organization of molecules within the cluster can go on changing. And to summarize all these things I have said so far, the failure of the functional group approach and variable interplay of kinetics and thermodynamics in the process of nucleation itself is the core issue. For example, looking at this picture, what do you see here in this picture? Do you see the picture of a man, or do you see fruits, vegetables, and flowers? Now, this is actually a fundamental issue. The smaller objects, the fruits, vegetables, and flowers, bear no relationship to the face of the man. You would not imagine looking at this flower or this vegetable or this fruit that when put together it will look like a profile and face of a man. So the larger cluster here is not modeled properly by the nature of the smaller clusters or the smaller objects. Many crystal structures are of this nature, and these are the ones that are difficult in crystal engineering. On the other hand, there are some where this is not the case. This idea of the supramolecular synthon, which I put forth in my article in Angewandte Chemie in 1995, has been a central idea in the practice of experimental crystal engineering ever since. Because this synthon tries to identify those cases where the larger clusters can be modeled properly with the structure of the smaller cluster. I told you in some cases it is not so easy, and these are the difficult cases for crystal engineering. Where the synthon approach works best is when the larger cluster can be modeled very nicely with the structure of the smaller cluster. The smallest of these clusters become then the common supramolecular synthons. And these are widely used. Generally, let me say that the smaller the synthon and the more widely it occurs, the more useful it is in crystal engineering. The larger the synthon, it may give a better approximation to the final crystal structure. But the larger the synthon, the less frequently it occurs. In the really good cases, if you find a large synthon that occurs very often, then prediction of crystal structures then becomes quite facile and easy. And these are the cases where crystal engineers are trying to look for all the time. And some of these nice examples in this last category have actually come in the area of the pharmaceutical co-crystals, which has become so very important in crystal engineering today. Now let's move a little faster maybe. And as I said, a synthon is really a practical concept. A synthon represents probability. The more often the synthon occurs, the more likely is it to occur in a future crystal structure which contains those same functional groups. And so the one to few to many to nucleus to crystal problem becomes to that extent much easier. Moving further, these analogies are very simple, and this is the original supramolecular analogy: atom to molecule, covalent bond to interaction, molecule to crystal. Now we can continue in the crystal engineering area: synthon to supramolecular synthon, synthesis to crystal engineering, isomer becomes polymorph, reaction becomes crystallization, transition state becomes crystal nucleus. In other words, crystal engineering is solid state supramolecular synthesis. These ideas were developed by me and several others in the late 1990s. And so you'll have a large number of papers from many people describing these ideas. Now coming to the interactions. Now this is, in a sense, I have finished the introductory part of my talk. Rapidly, I want to go through some examples. As I said, crystal engineering consists of three parts: interactions, their understanding, and their use. So these are the typical interactions. We've talked about hydrogen bonds, the CH pi, which is a kind of hydrogen bond if you think about it, a kind of, which we saw in the 3-aminophenol, 4-aminophenol case. And this is, of course, the van der Waals interaction, dipole-dipole, and the newer things that look like hydrogen bonds, halogen bonds, chalcogen bonds, nicnogen bonds. I mean, each of these interactions would require a full lecture of 1 hour. So since many of these words are known to many of you in the audience, with some of you actually working in great detail on one or more of these interaction types, I mention them here only for the sake of completeness. So this is the hydrogen bond itself. My name has been associated extensively with this interaction, especially the weaker varieties. And several papers have been written by me and others on this particular interaction. I'll say no more in this short lecture. Now, how do you use these interactions to design crystal structures? Look at this word retro. Retro must come into the picture because the synthon is a retrosynthetic approach to designing a molecule or a crystal using inductive logic. So, going back to Kitaï-Gorodsky and van der Waals interactions, organic crystal structures are predominantly governed by close packing and geometrical arguments. But, and this is a very, very important but, minor deviations from close packing which owe to chemical factors are of the greatest importance. And this is very characteristic in a complex system. When a minor deviation can cause the biggest changes, the whole response to the molecular change is, at least to our feeble minds, creating a huge difference. A small difference in the molecular property causes a big difference in the crystal property. This is an issue that we face again and again and again in crystal engineering. And interaction directionality then, far from being a problem, is a handle that permits crystal design. So these minor deviations are used as synthetic tools. This ties up also with the issue of polymorphism. We have many systems where we have the same types of interactions which blend together in different ways. For example, here is a co-crystal of para-hydroxybenzoic acid and bipyridine, where one of the forms is the one where hydrogen bonding is more important, and the one of the forms where the hydrogen bonding is more important, form B, and form A, where close packing is more important. And so the hydrogen bond form goes into the close packed form at higher temperatures. This is very common. And this is one of the reasons why you get polymorphism even when you have the same interactions that blend together in different ways. It's a kind of a compromise between interactions that leads to different crystal forms. So various people have written about synthons. And here is one from Professor Dunitz and Professor Gavazzotti, when they talk about the validation of synthons and the ranking of the intermolecular interaction energy. So once again, people are trying to understand interactions in the context of crystal packing. Moving on quickly to the halogen bond. As I said, it's a kind of hydrogen bond. We have an article in Accounts of Chemical Research where we talk about the halogen bond as being like the hydrogen bond, but not exactly. And what is the reason that the halogen bond is like a hydrogen bond? It is because in both cases there is an electrophilic atom. In the case of the hydrogen bond, the electrophilic atom is hydrogen. In the case of halogen bond, it's halogen. So if you look at the crystal structure of gamma hydroquinone, here you have hydrogen bonds. So with the same topology, you have the structure of 1,4-dichlorobenzene. So we call such structures, supramolecularly they are practically the same. And remember I told you about CH pi. So when you have 1,4-diethynyl benzene, once again the same topology. So here we have an electrophilic acetylenic hydrogen which goes to a nucleophilic triple bond. Again, electronically this is the same as this hydrogen bond and it's the same as this halogen bond. So the key factor in a halogen bond is an electrophilic halogen atom. And this is what was highlighted in the IUPAC definition of the halogen bond, where we pointed out that the key feature in a halogen bond must be an electrophilic halogen atom. Now, I've talked to you a little bit about how it's difficult to predict crystal structures on the basis of molecular structure. I present a small example which I must confess, even I don't understand very well. It's a case of a sort of a frozen molecular modularity in a crystal. If you take this 3,4,5 trichlorophenol, it looks like this molecule, this pink color thing here, is the elements of 4-chlorophenol. And this blue thing is, for example, 3,5-dichlorophenol. So it looks almost like that there are molecular features of 4-chlorophenol and 3,5-trichlorophenol in the same molecule. I mean, think about it again. It's like two molecules pasted into the same molecule. Now, we had this molecule with us and we determined the crystal structure. But for the life of me, I wouldn't have been able to predict the way this crystal structure turned out. Look at the crystal structure of 4-chlorophenol first. This is a classical phenolic group tetramer, and then these halogen atoms are connected with halogen bonds with other such tetramers. So this is 4-chlorophenol. Now when you look at 3,5-dichlorophenol, once again you have phenol-phenol hydrogen bonding, but you also have Cl2O dipolar interactions. It's a kind of a halogen bond. So the respective synthons are this tetramer here and this mixed synthon with hydrogen bonding and halogen bonding here. And here is one which has just got the halogen bonding part similarly and the hydrogen bonding. So you see, these synthons are all similar to each other. A collection of sort of fused tetramers. When you look at the trichlorophenol, this is the surprise. You see a part of the 4-chlorophenol structure reproduced with complete fidelity, and then you see the dichlorophenol structure reproduced with complete fidelity. Now this means that during the crystallization, at least in this part, it behaves as if the 3 and the 5 chloro groups are not even there. And out here it behaves as if the 4 chloro group is not even there. It almost seems that a part of the molecule is switching itself on and off in its supramolecular association. Cases like this is the only one we found of this type. Maybe some of you in the audience have seen similar examples, but this is surely the kind of thing that one doesn't go searching for. It just happens. The thing is to be watchful enough to identify things like this when they do happen. These are all problems for the future. Why does 3, 4, 5 trichlorophenol crystallize the way it does? My final example has to do with a practical case of crystal engineering. And this is the building up of co-crystals and higher co-crystals. Now, when you take 4-hydroxybenzamide, this one, it forms the typical OH hydrogen bond synthon, similar to the other phenols we have seen in this lecture. And if you crystallize it with an acid, this is a very stable and common synthon, the so-called heterosynthon, formed by a primary amide and a carboxylic acid. Very common. And so you see, using the commonness, the technical word that we use is robustness. The robustness of this synthon is such that when we take a primary amide and a carboxylic acid, we can be reasonably sure that this heterosynthon will be formed. So we have the strategy here to make a binary co-crystal between a dicarboxylic acid and a primary amide. That's what we've done. We've made a binary co-crystal. Now, let us take another synthon, which is formed from halogen bonding using the iodo-nitro interaction, the oxygen atoms of the nitro group. This is electrophilic, this is nucleophilic. So this is a halogen bond, which is bifurcated. So this is actually 4-iodo-nitrobenzene. This is a single component crystal structure. But you can make a binary from this by taking 1,4-diiodobenzene and 1,4-dinitrobenzene. And so you have a synthon similarity between these crystal structures. So whether it is a 1-component crystal or a 2-component crystal, these two crystal structures are what I would call supramolecularly equivalent. So what did we do? We took an acid and an amide and made a binary. Then we took an iodo and a nitro and we made a binary. Now you take these two ideas together. Suppose you take para-nitro-benzamide and crystallize it with diiodobenzene. The synthon carries over. In other words, the same combination of functional groups in two different molecules results in the same synthon and a similar crystal structure. So once again, we are going from known principles. This is an amide homodimer, amide. And then we have an iodo-nitro. Similarly, if you were to take the same amide and take para-iodo-benzamide and crystallize it with dinitrobenzene, we again get a similar crystal structure. So it doesn't matter on which molecule the iodine is and which molecule the nitro is. The crystal structures that you get are going to be similar. Now I think you can kind of understand what I'm going to get at now. What you do is now the final step towards making a ternary co-crystal And ternaries were something that came into our cognizance only about 20 years ago. But they were more actively identified by my group and a few others starting about 15 years ago. The basic strategy, again, since I've told you the component bits, is that you use this amide, primary amide, clubbing it with the iodo-nitrosynthon, and then you add the carboxylic acid here, because we know this is a good synthon, the heterosynthon. We know this is a good synthon. So we've got 1, 2, 3 different kinds of molecules which come into the same crystal structure. So we can build up this way from a single component crystal to a binary crystal to a ternary co-crystal. And these ideas can be taken further. And we have done so when we can go up to quaternary and even 5-component and 6-component crystals, where the molecules are located in stoichiometric amounts. Please remember, these are not solid solutions. And we have several papers in this area. I'm just mentioning this for the sake of completeness. And we have an article in Accounts of Chemical Research where we go from a binary to a ternary to a quaternary. And we have about 30 or 35 quaternary crystal structures from our group, which is the largest number of quaternary structures from any single research group in crystal engineering. This is now, as I told you, crystal engineering is a difficult subject. So selection, picking these molecules, crystallizing them is not the easiest of tasks. But what I want you to remember really is that getting 4 organic molecules in the same crystal in stoichiometric amounts, this is the important part. So you have 4 different molecules in the same crystal in stoichiometric amounts. Now this is something that is really quite difficult to do. And it requires extremely careful selection, because you just can't take any 4 molecules and put them together and hope to get a quaternary. Chances are that you will get a mixture of binaries, ternaries, or even single component crystals. So unless the molecules are very carefully chosen, the interactions between them are carefully calibrated, you will not get a quaternary crystal properly. And for those who are interested in some of these higher co-crystals, you should definitely read our paper in Accounts of Chemical Research and the full papers in Angevante, JAX, and IUCRJ. So where do we really go from here? I've talked about interactions. I've talked about understanding these interactions, van der Waals or otherwise, how they blend with each other, how synthetic strategies are developed in the light of the general problem that higher clusters may not be modeled easily on the basis of the structure of the lower clusters, and why this leads to the definition of the supramolecular synthon, which identifies those cases where such modeling is possible. Now, the subject of crystal engineering has really grown since the early days. And in a review article in Angevante, we are now moving from crystal engineering to actually property engineering. The third phase of this subject is definitely now fully upon us, where structure is almost a root to a property. And people are asking interesting questions as to whether properties always correlate one-to-one with structure. In the same way that a crystal structure does not correlate one-to-one with a molecule, does a property have to correlate one-to-one with a structure? We don't know. Sometimes it does, sometimes it doesn't. And 5 areas are of great importance now: pharmaceuticals, drug co-crystals, tableting, bulk crystallization. It's a huge area in itself. I told you crystal engineering has led to many sub-disciplines today. These are 5 important ones. Solid state reactions, co-grinding, industrial processes. See, these solid state reactions, let me tell you, ladies and gentlemen, is actually much older than crystal engineering. It's a very old subject, but has not been studied properly at a molecular level. So you may feel that here is something which is actually of industrial importance, because this also touches the matter of green chemistry. If you can carry out reactions without solvents, then you have properties: thermosalient materials, actuators, mechanical devices, smart materials. In general, the large field of mechanical properties of solids, a huge subject today. Many people are working in this area. But once again, let me tell you that these very interesting properties are once again manipulated, controlled, engineered by playing upon the way in which different kinds of interactions interact with each other. Once again, a characteristic of a complex system. Then we have the huge area of framework solids, MOFs and COFs. This is also formed by a kind of molecular recognition process. Once again, we are thinking about how to use interactions. Professor Robson in Australia is the one who really put this subject on the map in the early 90s, at about the same time when I was doing my work on supramolecular synthons. It's a kind of retrosynthetic approach, the same that I have used, but using coordination bonds. And finally, we come to even more modernistic areas: property engineering, solar energy harvesting, water splitting, and polymer science. And it's very difficult to predict where science will go. And I will not hazard a guess. But all that I have seen in the last 40 years, where I have been involved with the subject of crystal engineering, I can only say that the progress that we have seen so far makes me fully confident that even while we may have miles to go, the future will become only more and more interesting. So it's like these high mountains, and I'm pleased to say that I took this photograph myself, and so it's not downloaded from some site. So here I am, situated here, for example, in the Indian state of West Bengal. So the second line of hills is in the Indian state of Sikkim. The third set of hills is in the adjacent country of Nepal, where technically is situated the third highest mountain in the world, Mount Kanchenjunga. Very difficult to get a clear day in this area, and I was lucky enough when I went to a small place called Darjeeling here that I could get this view very early in the morning. And believe it or not, although it looks right close by, this is a clean 160 kilometers from where I was standing. So high is this mountain that 160 kilometers looks like just next door. So here we are, and I hope I've given you a flavor for some of the developments in the earlier days of crystal engineering, when we had to do all the things at the same time. understanding the interactions, developing a synthetic strategy around them, and making useful solids with useful properties. The lessons learned from the earlier days are still valid today. The most sophisticated of materials that people are trying to make today still use the same kinds of interactions, the 4 or 5 that I mentioned: van der Waals, hydrogen bond, halogen bond, etc. And the nature of these interactions has not changed. It is just the way in which we use them and the properties which we are trying to get that are looking different. The dynamics issue also has come in some of these cases. And therefore, this is a case where the fundamental principles, the basic things, continue to be always relevant. I only regret that I'm not able to be in Belgrade with all of you to share in the other lectures, the posters, and the several other scientific activities that must be going on. I thank the ICNI for having given me the Senior Van der Waals Prize. And the best kind of recognition that an academic can get is recognition from his or her own peers. In this sense, I am deeply grateful, and I wish all of you the very best in your scientific endeavors and to take this subject to further heights and even more exciting results. Thanks very much, all of you, and namaste.